Hello everyone, thanks for joining me today. My name is Peiyuan Li. I'm a PhD candidate from School of Sustainable Engineering and the Built Environment in Arizona State University. The study I'd like to share with you today is a data fusion approach to model the biogenic and anthropogenic CO2 exchange in urban area. According to the statistics from United Nations, the urban population has increased nearly six-fold in the past 70 years. By the end of 2050, more than two-thirds of people in the world is estimated to be urban dwellers. The concentrated population makes the cities the hotspot of greenhouse gas emission, especially carbon dioxide, which is a common believed contributor to the global climate change. To reduce the impact of human activities, cities have made great effort to reduce the carbon emissions, such as the transition to electric vehicles, use cleaner solutions to replace fossil power plants. The reduction goal needs policy engineering measures to fulfill, but also need the support from urban research communities. Here comes to an interesting observation. Most urban CO2 studies focus on anthropogenic sectors. The current advancement is remarkable. For example, the Hestia project estimates the traffic release of CO2 at 1 by 1 kilometer hourly resolution. We were able to make, I call it, the heart rhythm of on-road CO2 emission. It reflects the two peak hours in the morning and the evening. Yes, emission from on-road traffic, power generation, cement production, and other anthropogenic sources are significant, but all the spatial graded data in the urban area only count the anthropogenic sources. When it comes to the net carbon flux of a city, carbon sequestration from urban green spaces are overlooked. Fortunately, the development of Urban Canopy Model, or UCM, provides us the opportunity to model plant photosynthesis in the urban environment, thus the biogenic CO2 exchange. UCM has gone a long way from a simple idea that the urban surface should not be represented by a flat surface. Instead, the urban canning was used to represent the city streets and blocks. The current generation of the model can reproduce the built environment with a fairly good accuracy in terms of energy flux, temperature, and humidity. The calculation schemes accounted for the plant function in street canning, such as in evaporative cooling and radiative shading. The figure on the left shows the shading effect from the street trees during daytime. This realistic setting of UCM makes the estimation more accurate when investigating the role of urban vegetation on the microclimate. To fulfill the gap of urban biogenic CO2 estimation, we propose a unified framework based on the current development of UCM and the newest CO2 mapping technology. Since UCM is good at resolving the energy fluxes, temperature, and humidity in urban canning, we use the output of UCM to feed the soil respiration model and plant photosynthesis model to calculate carbon assimilation rate and the soil respiration rate and the urban environment. These altogether are the biogenic CO2 exchange. For the anthropogenic emission, the spatial graded data is readily available and adequate to match the resolution of UCM. For the long-term simulation, we use remotely sensed vegetation index and land use data to identify the plant phenology. Combine these together, the model is able to give the net CO2 exchange over the urban area. In the next few slides, I will briefly show a case study using the proposed modeling framework. The study area we select is a typical residential area in Phoenix. Phoenix has desert climate with extreme hot summer and warm winter. The population density of the area is roughly 1,650 persons per square kilometer. An eddy covariance system was deployed in 2011. The image on the right shows the area and the 90% of footprint of the EC tower during daytime. With a long-term averaged footprint, the line has 26% of building, 22% of road, 5% of tree, 10% of grassland, and 37% of bare soil. The study period is from the beginning of 2012 to the mid-year of 2013, considering the data quality and reliability. The eddy covariance tower is 22 meters. It measures the basic meteorological variables, such as temperature, incoming radiation, and wind speed. These will be used as the input for UCM. It also measures the energy fluxes and total CO2 fluxes, which will be useful in model calibration and validation. UCM is set up firstly and calibrated according to the measurement of the energy fluxes. The tunable parameters include albedo, emissivity, thermal properties of the building, and the ground materials. The top figure shows the time series of the measured and modeled energy fluxes in calibration phase. The bottom figure shows the scatter plot when compared simulation result to observation at 1:1 scale. The RMSE of the model is comparable to the other UCM studies. After calibration, these parameters are applied to the all study period for model validation. The model maintained a good performance throughout the study period. For a year-long simulation, we modeled the urban environment reasonably well. Then we proceed to the plant photosynthesis model and soil respiration model. Figure shown here is a CO2 release and uptake from the urban green space. This is January to June, and then July to December. The total uptake is purely from the vegetation, while the total release is a summation of soil respiration and plant respiration. Normally, the vegetation alone is net CO2 sink. However, the bare soil fraction of this study area is very large, leading to undesired CO2 emission. Then we move to the anthropogenic CO2 exchange. The hourly anthropogenic emission of the study is derived from the Vulcan CO2 map. Since the study area is residential, only on-road traffic is taken into account. The hourly afflux of traffic CO2 from Vulcan is estimated based on the local traffic count. On the right is the hourly emission curve. On weekend, we see two distinctive emission peaks. During weekend, the peak is less apparent. CO2 from human respiration can be a large portion of total emission for densely populated area. We use a simple equation to calculate the average human respiration, which is the population density times the tidal volume times the average CO2 concentration per breath times the number of breaths per day. Then the hourly change is estimated using the releasing factor. The figure here shows the different timing of human respiration for urban core and residential area, which basically accounts for the population density change within a day. When the anthropogenic emission is added into the biogenic sector, we can derive the total CO2 exchange from the urban area. Figure shown here is a diurnal cycle of CO2 flux in each season. We compare the modeled value to the observation. Over the study period, the model RMSE is 0.21 mg per meter squared per second. In the diurnal cycle, two emission peaks are captured. The model shows better performance in spring, summer, and autumn seasons. The RMSE is below 0.1 mg per meter squared per second. The model discrepancy in winter is larger. One is because of the large uncertainties in winter measurement. The other reason for the underestimation might be because of the release from the fireplace for room heating in winter time. Lastly, the figure shown here is the seasonal change of CO2 flux along with its decomposition. The thick red lines are the total CO2 flux. As mentioned before, the model performance is better during hot months. The numbers on the bar shows the percentage of each component. For example, soil respiration in May takes 32% of total CO2 release. Over the study period, traffic is the greatest source of CO2, followed by soil respiration. In some months, the amount of CO2 from soil respiration is comparable to the traffic release. Similar situation is reported in the other publications when looking at the residential area. So this is a good example that carbon emission can be reduced from non-anthropogenic sectors. In Phoenix's case, reduce the bare soil land is a good action. Besides, though the vegetation fraction is not very large, the plant sequestered a quite amount of CO2 in summer. Since urban plants help cool the city during summer as well, they may have the environmental co-benefits in heat mitigation and carbon reduction for hot cities like Phoenix. The hypothesis is waited to be examined in the near future. So in this study, we quantified the total urban CO2 exchange with good accuracy and identified the source and sink of CO2 in the study area. The modeling framework can cooperate with other modeling tools for further urban studies. For example, traffic emission in street canyon will elevate the local concentration of CO2, which fertilizes the plants. This effect might increase the power of CO2 sequestration. Now the model only predicts flux, but if combined with the flow field simulation or sub-canyon scale CFD analysis, it can resolve the CO2 concentration, so the hypothesis of the local CO2 uptake enhancement can be tested. If we look at the greater scale, UCM can be coupled with regional scale climate models, such as WRF model, to produce regional CO2 exchange estimation. This probably will gain our understanding to the role of cities to the global climate change. That's all from the presentation. Thanks for your attention. If you have questions of this study, please contact me via email or join the Q&A session during the conference.